Well, I want to talk about Isaac Newton. Here he is. This is Newton. This portrait is called Newton in his own hair. We're used to seeing him with the wig and the buckled shoes and the style of the day, but this is the man himself, and that kind of impressive face, I think. Here's what's going on tonight. A few years ago, I thought I would spend my summer reading the Correspondence of Isaac Newton. Tried to get a handle on this guy by reading the letters. And these have been collected by Cambridge University Press in 7 volumes. I brought one. This is a big. And 3,000 pages total. And these have in it all of the letters that he wrote and that were sent to him. And this talk is essentially his greatest hits, according to me, from what I enjoyed there. Now, I should just mention that this is in contrast to the mathematical papers of Isaac Newton, also published by Cambridge, 8 volumes and 4,000 pages. So if you want the complete Newton, there's 15 volumes and 7,000 pages. Now, what I want to do then is talk about letters throughout his career, letters from Cambridge, where he was a student and a professor. There's some letters from London, where he became an administrator. We'll talk about that. There's letters from the priority dispute. As you probably know, he and Leibniz get into this horrible spat as to which of them deserves credit for the calculus. And then I'm going to focus at the end on his greatest passage, that statement that if I have seen further, I have stood on the shoulders of giants. And where is that? And what's the story behind that letter? So all of these will be part of the focus, but when I ran this by Ivers initially, he says, you can't do that without doing some math. This is the Mathematical Association. So somewhere in there I'm going to slip in a little math as well. It's not terribly sophisticated, but it's extremely clever. It's Newton's use of the Generalized binomial series. And wait till you see that. It's one of his early discoveries. Well, this is Cambridge, where he was. This is Trinity Great Court, it's called. This is what it looks like now. It's basically what it looked like when he was there. It is, in my view, the most beautiful academic spot in the world. And Cambridge is unrivaled. He went there in 1661, and the earliest letter in his collection is from that year. And it's a letter to a friend. So here comes Newton's first letter that we have. Now, the friend had been reported inebriated. So Isaac writes to his friend and says, I earnestly desire you first to repent of your having been drunk. And if it please God that you ever be well again, then have a care to live healthfully and soberly for time to come. So right from the get-go, he's a scold, right? He's 19 and he's writing this letter. So you begin to get a sense of the character of Isaac Newton. All right, so this is his first letter. So what else is he doing in Cambridge when he's not scolding his friend about it over drinking? Well, he's doing a lot. As you may know, his years at Cambridge as a student were among the most productive years that any human being ever had. And they often say the periods 1665 to 67 were his Mirabilis, his miraculous years. He's working in isolation in his chambers, in his rooms at Cambridge. Nobody knows him. He's not famous. But what's he doing? Well, he discovers the generalized binomial theorem, which I'll show you. He invents fluxions, which we call differential calculus. He invents inverse fluxions. That's inverse calculus. He discovers the laws of motion. He works on optics. He does all this in complete isolation, in complete obscurity. And yet, if you look at this, you see he's charting the course of modern science alone in his rooms. It's been said that if the scientists of Europe knew that he was doing this, they would have been in awe, but nobody knows. How's he do it? Well, he has an IQ that, 3 digits, 4 digits, 5 digits, who knows. He's very smart, but he also works intensely, and he has this ability to concentrate on his work in a way that most people don't. There are reports that it would be evening. Newton would be sitting there writing. The candles were high. Someone would come back the next morning. Newton is still there. He hasn't moved. He's still writing. But the candles have burned low. He would forget to eat. He would forget to bathe. He would forget to sleep. This passion would just overwhelm him. And it was said that his cat grew fat, eating Isaac's untouched meals. Now, he also experimented upon himself. He was a good subject. And here's a letter where he's talking about his early experiments with vision. And you know, back then, vision and light, sort of the biological and the physical phenomena, were sort of studied together. So here's what Isaac tells us. I looked a very little while upon the sun in a looking glass with my right eye, and then turned my eyes into a dark corner of my chamber. So he wonders, what happens if you stare at the sun for a while? So he's got this mirror, and he looks in the dark corner, and he tells you that it's amazing what happens. You know, there's purple flashes and orange flashes. You know, it's really spectacular. And then he goes on in the letter and says, by keeping in the dark and employing my mind about other things, I began in 3 or 4 days to have some use. So you know, this is not wise to do this. Now, the most famous example of this, you probably have heard of this, is from his notebook. This is a page from his notebook. And right here, it says, I took a bodkin. This is a famous bodkin story. Now, a bodkin, if you don't know, is like a little sharp stick. And someone has said, think of a nail file. So I took a bodkin, he says, and put it betwixt my eye and the bone as near to the back side of my eye as I could. So that is, he's taking this nail file and sticking it behind his eyeball, so as to make the curvature A, B, C, D, E, F in my eye. So here's his hand, there's the bodkin, and there's his eye. Curve. And then he says when he starts pushing it, he gets these circles, R, S, T, U, and V up here, and the more he pushes, the darker they are. My sense, and this, I can't prove it, but I think at this point his cat agreed. So, you know, this is new. This is a passionate learner, sure. Now, throughout all this, remember, he's working in complete obscurity, but he claims not to want fame, not to want to get involved in controversies, to just keep to himself. And a letter to Collins in 1669 says, I see not what there is desirable in public esteem, were I able to acquire and maintain it. It would perhaps increase my acquaintance, the thing which I chiefly study to decline. If he was famous, he'd have to meet people, he'd have to deal with people, less time for his work. And he was not particularly eager to meet people. Now, in spite of the fact that he's not published at all, he becomes, in 1669, at age 27, the Lucasian Professor at Cambridge. This was the biggest position at Cambridge. And one of the questions is, how did this happen? How did someone who was obscure beyond the campus gates get this great position? And the answer seems to be that he was recommended by the previous occupant of that, Isaac Barrow. Barrow knew young Newton and knew how good he was. And he wrote that we should take a fellow of our college, and very young, but of an extraordinary genius and proficiency in these things. And based on Barrow's recommendation, Newton becomes Lucasian Professor. One of his duties as Lucasian Professor was to give a public lecture every once in a while. And he was terrible. Terrible. An eyewitness account. So few went to hear him, and fewer yet understood him, that oft times he did in a manner, for want of hearers, read to the wall. And he was obliged to give the lecture even if no one was there. Now imagine if Isaac Newton were giving a distinguished lecture in the carriage house. Now the place would be packed. Not then. The next year he invents the reflecting telescope, which for most anybody else would be a lifetime achievement. This is one of the crumbs that falls from his plate. But this, is the kind of telescope with a mirror at the end. He figures out how to do it, and then he does it. He actually grinds the mirror and builds the little tube. He was very good at mechanical things like that. He sends it down to the Royal Society in London, and now this is like his first public splash. And they love it. They make him a member of the Royal Society. And so he sends them something else. I guess he's starting to feel, maybe I can share some of this. He sends them some papers on optics. And these do not meet with the same enthusiasm. Robert Hooke, who was the giant of London mathematics and science, objects to some things. And now Newton responds badly. Right? he says, all right, I desire that I may be put out from being any longer a fellow of the Royal Society. Okay, he's just been admitted, he wants out. And later on, when he explains why, he says, I could wish I had met with no rudeness. So this criticism he receives, he took to be rude. He didn't want to get into this. He didn't want to deal with it. Well, the letters continue, and in the 1670s, he starts a correspondence with Leibniz. There's a little correspondence. In 13 June 1676, Newton sends to Leibniz what is called the Epistola Prior, the first letter, in which he talks about the generalized binomial series, the sine and exponential series show up in there as well. Leibniz in Germany responds on 17 August and asks for more, and Newton replies in the Epistola Posterior of October 24th, 1676. So as we talk about the priority disputes about who deserves credit for calculus, these are used as evidence by the British of an exchange of ideas. At this point, Newton, characteristically, is tired of talking to Leibniz, and he says, I hope this will so far satisfy Mr. Leibniz that it will not be necessary for me to write any more on this subject. I'm done. Now, let me give you the math here. What is this? The Newton's generalized binomial theorem, which he discovered early in his time at Cambridge, 1664 to 65. And let me show you what it is and how cool it is, what a neat application he makes of it. Of course, a binomial, two terms, like 1 plus x. You might want to square it. 1 plus x squared, which means 1 plus x times itself. And then, there's the old FOIL method. You do the inners and outers and all that. You get 1 plus an x plus another x plus an x squared. Sure, 1 plus 2x plus x squared. So there is how to expand, if you will, that binomial. Okay, so that's easy. But then the question always arises, what if you have 1 plus x to the 17? Now, you do not want to do it this way, I promise. We take 17 of these and multiply them all together, and that's where the usual binomial theorem comes in. So the basic statement of the binomial theorem is if you take 1 plus x to the r, you get 1. You get r x's. How many x squareds? Well, you get that. R times r minus 1 over 2 times 1 x squared. How many x cubes? The pattern continues, r minus 1, r minus 2 over 3 times 2 times 1x cubed, and so on. So, if you're a math teacher or you're up on math, you know this, of course. Maybe, even if you're not, you've seen this at some point. This is the binomial expansion. Hey, if you use 2, let's try to square 1 plus x using this formula. Well, you get 1 plus 2x, and then you get 2 times 1 over 2 times 1x squared. And then look, the next term, you get 2 times 1 times 0 as you reduce, over 3 times 2 times 1, x cubed. The next one will be 2 times 1 times 0 times negative 1, over 4, 3, 2, 1, x cubed. And what happens is, as long as you get a 0 in there, all the terms from there and rightward are gone. And then the 2 times 1 hits the 2 times 1, and of course you get the same answer. All right, so let's look at that and try it with 17. What is 1 plus x to the 17th? Well, you just plug in 17. So there it is. You get 1 plus 17x, 17 times 16 over 2 times 1x squared, 17, 16, 15, and so on. And, you can multiply these. Cancel. There's lots of canceling that goes on. So there's how it starts. 1 plus 17x plus 136x squared, and so on, and all the way down to when it grinds to a halt at 17x to the 16th plus x to the 17th. And that's much easier to do it that way, trust me, than to multiply these things 17 times. So, okay. Now, if you're in high school pre-calculus class or something, you run into this, they always ask this kind of question. What's the coefficient of x to the 11th in the expansion of 1 plus x to the 17th? And, these smart people will know the binomial expansion, and they'll just shoot right to the x to the 11th term. Use the pattern there. So here's what it would look like, right? You'd have an x to the 11th. If you look at the denominator, it's just 11 times 10 times 9 times 8, and on the top, you start with 17 and descend 11 terms. So it's not as hard as it sounds, and in fact, it gets a lot easier because things always cancel like crazy, and then you can take the 3 times the 5 into the 15 and all that, and I got it to be 12,376 x to the 11th. That's pretty neat. You can do that fast. Now, this notation, you probably know this 11 times 10 times 9 business. Usually, we just write like 4 times 3 times 2 times 1 this way, 4 factorial. And this is the way you tell the difference between people that know math and people that don't. I'm sure you all know this. If you know math, you see this and you say 4 factorial, and if you don't, you see this and you say 4! So, with that convention then, here comes the binomial theorem. 1 plus x to the r is 1 plus rx plus r times r minus 1 over 2 factorial x squared. R times r minus 1 times r minus 2 over 3 factorial x cubed, and so on. Okay, now all of that was known before Newton. That would have been known. Here's what he says. That this expansion remains valid even if r is not a whole number. The only examples I've shown you thus far, it's got powers of 2 or 17. But Newton says this is going to be good, and r could be integral or, so to speak, fractional, whether positive or negative. He says use it. It's still good. And hence the name, the generalized binomial expansion. Okay. So let me just remember, again, not knowing quite what the background is. What's a negative exponent? If the exponent were negative, x to the minus n, of course, is 1 over x to the n. So 3 to the minus 2 is 1/9. So that's a negative exponent. A fractional exponent, x to the p over q, is the cubed root of x to the p. So, 8 to the 1/3 is the cube root of 8. Now, when Newton would write about this initially, he would have to explain this, because it wasn't taught in pre-calculus classes at the day, so you had to sort of remind people what these fractional or negative exponents were. Okay, now, there's the big formula. And now he says, all bets are off, r could be a fraction. And so let me give an example. Let's expand the cube root of 1 plus x, a la Newton. He would write this as 1 plus x to the 1/3. And he says, I'm going to go to this formula and just stick in 1/3. Okay, so here you go. You get 1 plus 1/3 x. Now, then here you get 1/3, and then you reduce it by 1. 1/3 minus 1, there's the 2 factorial. 1/3 times 1/3 minus 1 times 1/3 minus 2, 3 factorial. On it goes. Let me put that up at the top here and simplify this. Let's see, that'll be 1 plus 1/3 x. The second term is 1/3 times negative 2/3 over 2 times 1. Here comes 1/3 times negative 2/3 times negative 5/3 over 3 times 2 times 1. And it's, not that hard to get the expansion. And there it is, as it starts off, 1 plus 1/3 of x minus 1/9 of x squared plus 5/81 of x cubed, and so on. And what's amazing here, it's an infinite series. You never get a 0, as we did with that 1 plus x squared, to stop it. It never stops. It just keeps going. And so, to Newton, we could expand the cube root of 1 plus x into this infinite series. This is how it starts. Now, he checked this by cubing the series. He says, let me take the series, multiply it by itself, and multiply it by itself again. And if you got 1 plus x when you cubed it, that would be confirmation. Well, amazingly enough, if you cube this, you get 1, you get 1x, you get 0x squareds, they cancel. You get 0x cubes, they cancel. You get 0x, all the other terms cancel. And that's not going to happen unless this is a minus 10 over 243. This is exactly what the doctor ordered. If you cube this, everything goes away except the 1 plus x. And if the series cubed is 1 plus x, the series is the cube root. So that was his confirmation. It's amazing. But there's more. He says extraction of roots are much shortened by this theory. So I can find roots. For example, suppose you want the cube root of 140. Now, suppose I asked you this. I say, I'm going to lock the door. I'm going to give you one sheet of paper, the pencil, in 10 minutes, and give me the cube root of 140 to 4 places. You'd say, how can I possibly do this? Well, Newton could, because he knew this generalized binomial expansion. So let me show you this. Now, there is a little danger here, and Newton realized this, that if you're going to use this expansion, the value of x must be small in order for this to, we would say, converge, to stabilize around the right number. Newton didn't use the convergence terminology, but he knew that you had to put in small x's to make this work. So, the first thing I would think of is if I'm going to do the cube root of 140, I'm going to write it as 1. If I'm going to use this, 1 plus something, 1 plus 139, but that doesn't work because 139 is way too big. If you try that, you're going to get a divergent series that's going to be crazy. Okay. So Newton knew that. So he said, okay, here's what you do. You use artifice. Trickery, we're gonna be tricky. So here's how he would go. There's the series. He's going to say, all right, I want the cube root of 140. Pick a perfect cube near 140. Right, 125. Right? So 5 times 5 times 5 is 125. So you break 140 up into 125 plus 15, factor 125 under the radical, and break this into two cube roots, the cube root of 125 and the cube root of 1 plus 15 over 125. Well, the cube root of 125 is 5, and this second term reduces to 1 plus 3/25. Now, with the artifice, you go back here and let x be 3/25, and you're going to get rapid convergence. And so, here we go. The cube root of 140, we said, is 5 times the cube root of 1 plus 3/25. I'm not going to use an infinite series, of course. I'm going to stop after 4 terms. So I'm going to put in, I'll just stop here with the 581st, but I'm putting in 3/25 as my x. Add those up and then hit it with a 5. Now, nothing here is too bad. There's some fractions, you cancel the 3's, and here's a 9. So you could do this in 10 minutes. And in 10 minutes or less, you get 5 times 9736 over 9375, and then you can actually cancel the 5 into the bottom. So there you go. Time's up. Your piece of paper, your pencil, 5 minutes, 9736 over 1875 is what you say is the cube root of 140, using Newton's expansion. Now, how good is it? Well, I got out my calculator and got this to be 5.19253. Then I got out my calculator and asked it for the cube root of 140, and it was 5.19249. So I'm off at 4 places in, 100,000? Yeah. It's extremely accurate. And you can be more accurate if you went out to this term. So this is elementary in some ways, and yet brilliant, and nobody was doing stuff like that. So that's why he says extractions of roots are much shortened by this theorem. And if you think about it, you don't need cube roots. You can use the same formula and do 4th roots, 5th roots. Just let r be a 4th or a 5th. So this is a surefire approach. He later says, I'm ashamed to tell you how many places I carry these computations, having no other business at the time. For then I really took too much delight. Now, there was more he did with series in this period. Let me just show you this one thing. Now, this is from a publication of Newton long after he did this. He would not publish things until long afterwards. But if you look right here, I don't know if you can see this. He says x is equal to z minus 1/6z cubed plus 120 at z fifth minus 1 over 5040 z to the 7th. Well, his x there is the sine. And right there is the sine series. He's got it. And, we call this the Taylor series or the Maclaurin series for sine. It's the Newton series. There it is. So, it is certainly the case that Newton's infinite series expansions were triumphs of the new mathematics and would be applied all over the place in the years to come. Okay, so that's my little math part. Now, back to the letters. Newton's writing to William Briggs, 1682, and he's in a grumpy mood again. I am of all men grown the most shy of setting pen to paper about anything that may lead to disputes. He says, I don't want to get into disputes. Not so. He seemed always to be getting into disputes in spite of this. And here comes one that a few years later, in May of 1686, Edmund Halley, of comet fame, writes to Newton and says that regarding the inverse square law of gravitation, Robert Hooke, down there in London, is claiming priority and wants to be recognized in the Principia. Now, the inverse square law, as you know, is the sort of fundamental idea upon which Newton is going to build his mechanics, explain how the planets move, how the comets move, create what he called the system of the world. And this is the big result of the inverse square law. The Principia he's writing to explain all this. And here's Robert Hooke saying, I thought of this. I want credit in the Principia. That's not going to go over too well. And so he writes back to Halley and says, now, is not this very fine? Mathematicians who find out, settle, and do all the business must content themselves with being nothing but dry calculators and drudges. And another that does nothing but pretend to grasp at all things must carry away all their invention. So he's saying that Hooke pretends to understand. Whoa. Well, when Halley gets this, Halley immediately writes to Newton and says, "Sir, I must now again beg you not to let your resentments run so high." But Newton's resentments were on a hair trigger and would run high all the time. I should say the next year he publishes the Principia, and no, he does not credit Robert. This book, of course, comes out in 1687. He gets a fan letter from David Gregory. Gregory says, "Your book is of so transcendent fineness and use that few will understand it." What a review, right? I'm reminded of Yogi Berra's comment about the restaurant that's so popular that nobody goes to. What does this even mean? Okay, so about this time, Newton goes to London. He is elected to Parliament, actually, strangely enough. And we think of politicians as being a little more gregarious than this guy. But he gets elected from Cambridge, and the reason is King James II, the Catholic king, has been kicked out of the throne. The Protestants are in with William and Mary. Newton was a staunch anti-Catholic. He wanted to support the Protestant takeover in the Glorious Revolution, so he stands for election and goes down to Parliament. Later in his career, he stood for re-election and lost. But it is said that his parliamentary career was a complete waste. That's almost true, but I did find this letter. In 1689, he says, "This day upon a motion made by Sir Thomas Clarius for Oxford, and by me for Cambridge, the House of Commons gave leave to bring in a bill to settle the charters and privileges of the university." So at least he had some impact on legislation. A few years after this, everything goes dark. Newton suffers what they call his black year, a year of depression, a year of lethargy for this most active of people. Nobody's quite sure what this is all about, but it was quite serious for a time. And let me show you two letters that indicate that. In 1693, he's writing to Samuel Pepys, the diarist, and Newton says, "I am extremely troubled at the embroilment I am in, and have neither ate nor slept well this 12-month, nor have my former consistency of mind. I must therefore withdraw from your acquaintance, and see neither you nor the rest of my friends anymore." Now, in the correspondence, there's letters from Pepys to somebody saying, "What's going on with Newton? What is this?" But a few days later, it gets worse, because he writes to John Locke, the great philosopher. And Newton says this, "Being of opinion that you endeavored to embroil me with women, and by other means I was so much affected with it, as that when one told me you were sickly and would not live, I answered 'twere better if you were dead." Wow. I wonder what John Locke thought here.
Philosophical.
Right. So, this is a tough time for Newton. And, it's not quite clear what it was going on. His mother had died recently. Maybe that was part of it. Maybe it was a midlife crisis. There is this suspicion that when he was working with chemicals, he would taste them to check their purity, and maybe he was poisoning himself. He did come out of this, and did apologize to Locke for this intemperate remark. He said, "Last winter, by sleeping too often by my fire, I got an ill habit of sleeping and a distemper, which this summer has been epidemic." So he gets out of his depression, but it was a strange little interlude. Well, in 1696, another amazing career change, he becomes Warden of the Mint, which at the time was in the Tower. Now, here he had to oversee recoinage, work with the bankers, but one of his responsibilities was to prosecute counterfeiters. And this he did. And there's a famous case of William Challoner, a counterfeiter, who had been sort of a celebrity criminal, I gather, as I read this. Somebody who kept getting caught, but wouldn't really get punished. He had counterfeited the Birmingham Groat. I know most people would be really offended by that. But whatever this was, he got off, and he was sort of a celebrity in London. And then Newton comes along, and Newton is not going to let him off. Newton oversees his prosecution, his trial. He is convicted to die. In And so Challoner now realizes that his time's almost up. He needs mercy. And he writes to Newton at the Mint and says, I am going to be murdered unless I am rescued by your merciful hands. Oh, I hope God will move your heart with mercy and pity to do this thing for me. I am your nearly murdered humble servant, William Challoner. And he sends this to Newton and hopes for a response and a reprieve. And neither comes. Newton ignores it. And 16 days later, Challoner goes to his death. So if you're looking for mercy, not there. Later in his life, Newton's talking about another counterfeiter and said, since he is evidently convicted, I am humbly of the opinion that it is better to let him suffer than to venture his going on to counterfeit the coin and teach others to do so. Okay, so that's warm and fuzzy Isaac, right? All right, let me talk about the priority dispute. The battle over the creation of the calculus, Newton and Leibniz, his great rival. This is Leibniz in somebody else's hair. Now remember, Newton had sent him 2 letters in 1676, the Epistola Prior and the Epistola Posterior, talking a little bit about his series work. Moreover, in 1676, Leibniz had actually visited London on a diplomatic mission and there saw one of Newton's manuscripts, the De Analysi. Newton would write up his stuff when he had discovered it, but he just wouldn't publish it. He'd put it in his desk, or occasionally loan it to someone, but make them promise not to publish it. And one of these manuscripts was in London, and Leibniz sees that. So this is going to figure in the case that's coming. In 1684, Leibniz, not Newton, Leibniz publishes the first paper on the calculus, and this is it. So this is how the world knows or meets the calculus. I'll translate the title in a minute, but just if you want to see the key word, it's right above my finger, calculi. There it is. And this is his paper, 1684. The title is A New Method for Maxima and Minima, and also tangents, which is impeded neither by fractional nor irrational quantities, and a remarkable type of calculus for it. And you can see from the title what he's doing here. We're talking about max, min, and tangents. This is his differential calculus. And the little d appears there, and the product rule appears there, and all that. And then 2 years later, he writes an integral calculus paper, and there's the integral sum. So, in terms of getting things in print, Leibniz wins. Well, Newton reads this paper, and he's a little put off. Newton's looking, where's my name? How come he didn't mention me? Well, in 1693, Leibniz tries to rekindle the conversation and writes to Newton and says, I write this rather that you should understand my devotion to you, a devotion that has lost nothing by the silence of so many years. And Newton writes back rather graciously and says, I value your friendship very highly and have for many years back considered you as one of the leading geometers of the century. Nevertheless, Newton is miffed that somebody else is getting all the credit. Now, as a fellow named Robert Merton writes about this, and he says, Newton, you will remember, had a way of not putting things into print until he was good and ready. And sometimes not even then. And so he was asking for trouble. I mean, he just should have published this when he first did it, and there would have been no controversy. And even his contemporaries realized this. John Wallis writes to Newton in 1695 and says, you are not so kind to your reputation and that of the nation, England, as you might be when you let things of worth lie by you so long till others carry away the reputation that is due to you, others being Leibniz, of course. Well, Newton gets more and more angry, and by 1711, he's writing to Sloane and condemning those who insinuate to their readers that the method of fluxions is the differential method of Mr. Leibniz, and do it in such a manner as if he was the true author and I had taken it from him. And someone named John Kyle writes to Sloane in 1711 and says, Newton gave such clear and obvious hints of his method to Leibniz that it was easy for the latter to hit upon the same method. And that was the British explanation as to how Leibniz beat Newton into print. Leibniz wasn't too happy with this. He says, I cannot bring myself to make a reply to that crude man, Kyle. And then Leibniz ups the ante. He writes, I have indeed observed no shadow of an argument, whence it appears that notice of the infinitesimal calculus came from Newton to me, for which reason we judge rather that it was not well enough known to Newton himself before I published. So that, I didn't steal it from him, he stole it from me. Come on. Well, Newton doesn't like this. He writes to Conte, and he's remembering back to that original paper, and he said, Leibniz understood in those days that I had a method which did the same things as the method which he calls differential, and he ought still to acknowledge it. But he has lightly attacked me with an accusation which amounts to plagiarism. So Newton is feeling slighted. Leibniz is feeling slighted. Newton goes on to say that Leibniz had hitherto written letters to his correspondents full of affirmations, complaints, and reflections without proving anything. But he is the aggressor, and it lies upon him to prove his charges. Well, we now know that both men independently created the subject. That, yes, Newton did it first, chronologically, but Leibniz did it before he was getting these letters from Newton and seeing the manuscript. So they both deserve credit for this. It's one of those ideas that was sort of ripe, and if you have two geniuses of this magnitude, it's not surprising they both discovered it. Leibniz dies in 1716, but Newton's not ready to give this up. And he's ready to demob. Now, it turns out, there's a curious little side issue here. In Leibniz's career, let's see, Queen Anne of England dies and has no heir. So the next person to take the throne is George, Georg of Hanover, to come in as George I, and that was Leibniz's employer. So there was this possibility, this was before Leibniz had died, obviously, there was this possibility that George would bring the court from Germany, and Leibniz would come along, and Leibniz and Newton would be in the same city, in London, because at that point, Newton's at the Mint, and then they could either settle their differences, or duke it out, at Spitalfields Market or something. But here's Newton's take on that, long after Leibniz is gone. He says, when the court of Hanover came to London, his friends endeavored to reconcile us in order to bring him over to London. But they could not get me to yield. Newton wasn't going to do it. And he writes to Varignon in 1721, this little episode. He says, Mr. de Mauve has told me that Mr. Bernoulli desires a picture of me. But he has still not acknowledged that I had the method of fluxions in the year 1672. If he will submit on those points so as to entirely remove the cause of the disputes, I will not readily refuse my picture. So he never quite gets over it. Although he does write to Varignon also, same letter, I've always avoided court. Okay, so maybe this is Newton at his worst. But let me end this with Newton at his best. And that's the great line about the shoulders of giants. It's in the Correspondence. I was reading this, as I say, a few summers ago. And when you look at February 5th, 1675, there's a letter from Newton to Hooke. Now, this was before their relationship completely disintegrated with that, inverse square law, put me in the Principia business. This was 10 years before that, 11 years before that. They were still at odds, but they were civil, at least. And in this letter, Newton seems to be wanting to smooth the waters some with Hooke. So he's uncharacteristically gracious here. Early in the letter, he says this, there is nothing which I desire to avoid in matters of philosophy more than contention, nor any kind of contention more than one in print. We've heard that before. And then he goes on and says something actually quite profound. Newton writes, what's done before many witnesses is seldom without some further concern than that for truth. But what passes between friends in private usually deserves the name of consultation rather than contest. So, Mr. Hooke, let's keep our disagreements in private letters as friends, and all will be well. Then he goes on and says, he's made great achievements, of course, but he's ready to share the credit. What Descartes did, writes Newton, was a good step. You have added much several ways. You, Robert Hooke. That's very nice. And then the next line, if I have seen further, it is by standing on the shoulders of giants. There's the great passage. This is the great metaphor from Newton, his most famous line. I would argue maybe the most famous line in the history of science, because it so perfectly and so poetically captures what it is science does, as you build upon the work of your predecessors. Now, that same Robert Merton I mentioned a while ago has written a book called The Shoulders of Giants, in which he points out that Newton didn't exactly create the metaphor. This has been around. In 1616, somebody named Godfrey Goodman had said, "We are like dwarves set upon the shoulders of giants, discerning little of ourselves, but supposing the learning and groundwork of the ancients, we see much farther than they." So there's that concept. And 2 years before Newton's born, George Herbert says a dwarf on a giant's shoulders sees the further of the two. So you can see that some of the idea was around, but Newton's is much better than this. For one thing, there's no dwarves in it. And it's much more poetic. So I'm willing to give Newton a lot of credit for his phrasing. It's such a famous line that it appears on British money. If you go to England now, this is their £2 coin. It's a beautiful bimetallic piece. And if you look on the edge, read around the edge, it says, "Standing on the shoulders of giants." And here's a few of them stacked up. You can see them standing on the shoulders of giants. So on all the coins, all the £2 coins, their favorite son, Newton, is being remembered. Okay, so I'm reading about this in the Correspondence. You know, I see this great letter to Hooke with the great passage. And I wonder, you know, where is this letter? Where would it be? All right, first guess, the British Library in London. I don't know if you've been there, but if you go in the British Library, there's this room that's like their Hall of Fame, where the Magna Carta is in there. The Magna Carta is in there. And, you know, there's first folio of Shakespeare, and there's manuscripts from Dickens and Austen and the Beatles. So, you know, surely Newton's most famous letter would be there. No. Okay, well, maybe in the Wren Library in Cambridge, his alma mater. And if you've ever been to Cambridge, go see the Wren Library. Christopher Wren designed it. It's beautiful. They have all kinds of neat manuscripts. No, not there. The footnote in the Correspondence says that this letter is in Philadelphia. It says it's in the Historical Society of Pennsylvania. I say, this can't be right. So I send an email, and I say, "Do you have this letter?" And they write back, "Yeah." And I say, "Can I come see it?" And they say, "Sure." Well, I live near Philadelphia. So at the earliest opportunity, I take the train, you go into Center City, you get off near Independence Hall, and you walk to this very striking building, the Historical Society of Pennsylvania. I go in, I clear security, I give them my little request for this letter, and they go back into the archives. And pretty soon, a librarian comes out with a manila folder, puts it down, I open it, and there it is. The letter. The original parchment, the original ink. Newton wrote this. And, you know, you're sitting there holding this thing. It was awesome. Right? It was awesome. And I mean, I spent a lot of time communing with this letter, sort of seeing Uncle Isaac, you know, with the candles burning and all. I mean, it was so neat. And you could read it. It was very legible. I mean, it was perfect condition. It was in something called the Simon Gratz Autograph Collection. I'll tell you a little more about that in just a minute. But here's the top of it. I managed to get a photocopy, and you can see it says Cambridge, February 5th, 1675. And you know, you can see that it's pretty legible, pretty readable. Well, down here, a little bit further, if you read down, you find it. And there it is, in Newton's hand. If I have seen further, it is by standing on the shoulders of giants. So there it was, the great passage. And so after half an hour, I reluctantly gave back the folder and went back into the archives. But then I had to ask, how did this land in Philadelphia? What happened? Who is this Simon Gratz fellow? Well, it turns out he was a Philadelphia industrialist whose hobby was collecting autographs, signatures of famous people. And he would buy them. And so he has a signature of Cromwell, Napoleon, George Washington, and all these people. And he wanted Newton. And so he bought this letter because it has Newton's signature on it. Now, I'm sure Gratz knew what he was getting. This wasn't just any old signature. But in a certain sense, the real reason this was bought was not that side of the paper, but on the back, where we find his signature. He signs off to Hooke, your humble servant, Isaac Newton. For this, Gratz buys it. His estate goes into the Historical Society of Pennsylvania. The letter is there now. I'm sure, the British notwithstanding, it will be there always. And the rest of us must content ourselves with standing on the giant shoulders of Isaac Newton. Thank you.